All right, so anything C1 through C6 is fine. I'm gonna shut this. I would say the physics word problems for today, I'm gonna punt just because the gateway on Friday is not really gonna get into the word problems. Those are more fleshed out kind of exam type questions. So I'm going to do this again on next Monday as well if people find this helpful. So next Monday would be a great time to bring that stuff up because we'll have more word problem sections between now and then, and it would kind of fit in with what we're doing about applications of derivatives. So if anybody's got anything ready that they want to talk about, I'll just kind of take turns going around the room and we can address people's questions and concerns. So I want to start us off. Yep.
How do you differentiate, like e to the 17x minus 3x squared?
So this, taking the derivative of something like that? Okay. So this problem is a combination of knowing the derivatives like that we were allowed to memorize, right? And most of these derivatives that we had to memorize involve functions with like letters in them, right? So, but this is also a chain rule problem. So I feel like if I told everybody in here, what's the derivative of e to the x, everybody would go e to the x, right? So this is a situation where we actually have, right? This is what I mean when I say if we have e to the u. So the derivative of the outside function is just e to the u, just like e to the x is. And then we multiply it by the derivative of the inside function. So that means we leave the function intact. So there's e to the u, and then we multiply by the derivative of the stuff that was inside. So 17 minus 6x. Is everybody cool with that? So derivative of the outside times derivative of the inside. If you wanted to split it up in your f and u notation, then f would have been e to the u, right? U would have been your 17x minus 3x squared, and then f prime would have just been e to the u, and u prime would have been 17 minus 6x. So it's derivative of the outside times the inside. So you want to make sure that every time we teach you a new derivative, the very first thing you'll notice we ask you to do in your workbooks is now apply the chain rule to it, now that we know the chain rule. So chain rule can sneak up on you from everywhere, every which direction. If y'all have any questions about anything I'm doing, it's not clear, this is the time to let's get everybody on the same page. Does this make sense? Okay. All right, what else? I know you have a list.
On web work, there was a problem that said given 2 points, find dy dx, and it was like the square root of x plus the square root of y equals 8, and the points were 9.
Okay, hold on. So square root of x plus the square root of y equals 8, right?
Yeah, and the given points were 9 and 25.
Okay, and they wanted you to find the derivative at that point?
Yes.
Okay, so the reason they gave you this point is because, believe it or not, this is an implicit function. Okay, so you have x's and y's right mixed together. We can't really solve this for y. The best we could do, when we could bring the minus 8x over, but if we squared it, I mean, maybe on this one you could get away with writing it explicitly if we put in the algebra. But the reason they gave you both points is they were hoping that you would see the way this is written implicitly. If you did implicit differentiation, you could find it. So if we did that, the derivative of this guy, right, is going to be 1 over 2 root x because it's 1/2 x to the negative 1/2, right? Same thing's going to be true of the y portion, right? It's y to the 1/2, so it's 1 over 2 square root of y, but we have to multiply this by dy dx because it's chain rule. So the derivative of the outside was this, the derivative of the inside is just dy dx. Then the derivative of 8 is 0. So if we solve this for dy dx, right, we move everything without a dy dx the other side. And I can see here that I've got a 2 in the denominator of each function, so that'll cancel. And if I want to get dy dx all by itself, well, we just multiply both sides by the square root of y. So this is our derivative. So you can see that we had x's and y's in the derivative. So if we want to evaluate this at the point, we needed both coordinates. Now another way I could have given you the same problem was I could have just said, find the derivative of this function when x equals 9. But then when you got here, you would see I need a y, and you would have to go back to the original function to find that y, and you would have had to solve to get your 25. But they were kind in this one and gave you both points. So it would be negative square root of 25 over square root of 9, and that should simplify into negative 5/3. And so this would be the slope, right, of your tangent line if there was like parts B, C, if we wanted to keep going with it. So it should make sense that, right, if the function starts out implicit, it's not surprising that we had x's and y's in the derivative as well, and that we would need both coordinate points to do that. Is that? Yeah, okay, okay.
So like for when you write dy dx like on the inside of the equation, it's only when it's like implicit differentiation? Okay.
So you take the derivative of any term with a y in it, just like you would if it was an x, right? But then we apply the chain rule. So that's what implicit differentiation is doing. It's saying the outside function is square root of y, and the inside function is y is some unknown function of x. So we're just going to call it dy dx. Yep. And so you'll tack that on. That's why today when we did those problems involving logarithmic differentiation, we always had to tack on the dy dx because that we were applying the chain rule. Yep.
So is it for like any chain rule you tack on the dy dx, or is that only for implicit?
Implicit, it's so for any chain rule, it's derivative of the outside times derivative of the inside. But for implicit differentiation, the inside function is invisible to us, right? It's just y is some unknown function of x that we can't see, so we just call it dy dx, right? But for this one, right, this was a chain rule where we could see the inside function, so it was not dy dx, right? Yep.
When you isolated dy dx, how did you get negative square root of y over square root of x?
So, well, first I had a 0 over here, and I wanted to get only things with dy dx, because this is just algebra after this. So I wanted to get only things with dy dx on this side of the equation, so I moved this to the other side. So when you subtracted, it became negative. And then when you were down here, we canceled the 2's, so then I multiplied by the square root of y on both sides, and that's how it ended up here. But the negative came from the subtraction in the previous step. And this step I did at the end is no different algebraically than what we were doing today when we had to multiply everything by y, right? Y was in the denominator, so we just multiplied both sides by y. In this case, it was square root of y in the denominator, and we just multiplied both sides to get it in the numerator. And back here, I'm just going to write, so we kind of have a running thing of what we're talking about. Yep.
How would you differentiate something like 5 to the 2x minus 3?
Okay, so let's get back here. All right, so you said 5 to the 2x minus 3, all in the exponent. All right, so what we have here right, is an exponential function that involves a chain rule, right? So we said, well, dx of any function a to the x, right, is a to the x ln of a. But now, if we want to apply that definition to the chain rule, right, U now stands for an expression, we'd get a to the U ln of a, there's the derivative of the outside function, times u prime. So to do your function, if I take the derivative with respect to x of this, the outside function is 5 to the u, right, ln of 5, and then I have to multiply this by the derivative of my inside function, which is just 2. And so what you absolutely cannot do here is you are not allowed to combine the 2 with either one of these 5s you see, right? That's not allowed. So I might, just to make this clean up a little bit, I might say 2 times 5 to the 2x minus 3, right, ln of 5. So there really is no kind of perfect way to write this. But you can't combine the 2 and the 5 because they're not raised to the same power. Does that make sense? Yep.
Is there any way to do, so like if you have just the simple derivative of x to the x?
X to the x?
Is there any way to do that without using natural log?
No. So there might be a way using the definition of, sorry, and I'm going to awkwardly repeat some of your questions because I want the camera to pick up the question, right? So it's not me being weird, it's just the camera. So you're welcome, people at home. Yeah, no, so x to the x, right? Logarithmic differentiation is the absolute most straightforward, easy way to do it. There may be a proof out there using the definition of the derivative, but it's probably really ugly and gross because it would be like x to the h raised to the x plus h minus x to the x. So I think somewhere I've seen it, but it gets, you got to pull some pretty wild algebra out of your habit. And I think even then with the limit, I think you still might end up having to introduce ln of x. Yeah, no, as a matter of fact, you do, because I've done that in sequences and series. So you still end up bringing in an ln or a log in it to get to separate the exponents down. Yeah. So now that so logarithmic differentiation, using that to prove something is a little bit of a cheat in a way because we're really supposed to use the definition of the derivative, right? And use the limit definition to prove all derivatives from first principles. But what we're doing is we're saying, okay, well, we know these functions have inverses, so we use the inverse and implicit differentiation, right? And with logarithmic differentiation, we use the algebra fact that we can pull the x down, and then really, once we've simplified the log portion of the problem, from there out, we're really applying implicit differentiation to solve the problem, yeah.
So if it was on the test and they said prove the...
If you see an equation, if you see an expression with an x, raised to another expression with an x in the exponent, logarithmic differentiation is really the only option you have.
And like if they asked you to prove the derivative, like would they or...
We would, like, I might say show the derivative. Well, no, not on something like that. We would just probably just say take the derivative, right? Now what I was getting at today was if I gave you an expression of that form, the instructions could be just take the derivative, and I'm testing you on, do you know that that is the appropriate method for this form? Or it could also say use logarithmic differentiation to take the derivative, but don't count on that. We can ask you to use logarithmic differentiation without ever using those words. We can just give you functions where that's required. Yep. And really the only thing where it's absolutely necessary is an x to an x. Yep. Yeah, go for it. I know you got a list running. She brought a list. Happy.
Can you go over like how to solve for the horizontal tangents?
Yeah. So did you have a particular question?
No, just like trying to get like a better understanding.
Okay, I can go through okay, so in that case, since the algebra moves are going to be really different depending on the problem, I can go over the process.
Yeah.
Okay, all right. Because it's sort of like what we did today. The algebra moves will vary, but the procedure is pretty much set on these, right? So, and remember, horizontal tangents are different than the process for finding horizontal asymptotes, because those are two different things. All right, so it kind of helps me to understand what algebra process I'm going through if I have some kind of visual to associate it with, all right? So on a graph, right, we know we can't take the derivative at sharp points, okay? So if the function's differentiable, right, it's going to look like a curve on the graph. So horizontal tangents are going to occur when the graph is turning from up to down, or when the graph has a turning point at the bottom. And we can see here that at this little maximum, which we're going to get into this a little bit later this week with the extreme value theorem, right, or here, we can see that that's what a piece of a graph with a horizontal tangent is going to look like, right? And this is why we care about them so much. So the example that we did back in section A was we had you use the properties of a quadratic to find the minimum product of two numbers, right? We gave you those two scenarios. Then we asked you, when we taught you derivatives, like the simple power rule derivatives, we brought that problem back and said, well, now find the minimum or maximum, right? In that case, minimum, using calculus. So the calculus way is, well, the minimum or maximum is going to occur when the tangent line's horizontal, because you're looking for the turning point, when the graph gets as high as it goes in that area or as low as it goes in that area. So we can see from this, since we know the derivative, right, is the slope of the tangent line, then when we want a horizontal tangent, right, we find dy dx or df dx, whatever the name of your function is. We set the derivative equal to 0. So if we know that the derivative is the slope, what we're doing is we're trying to find, well, where does this function have slope 0, right? Where is the derivative equal to 0? So then we solve for x. And if we want a point, so if you want the point on the graph, then you plug the x value into the original function. We almost never ask you to give us the equation of the tangent line at that location because it's just so rudimentary. The tangent line is just a horizontal line. So that's just y equals whatever the y coordinate is of that point, right? So that's why we usually say, where on the graph does this occur? So you find the locations, right, of the x's where the derivative is 0. Then you plug those back into the original graph, because what you're trying to do in that case is find the actual location on the graph itself of where this is occurring. And we may not always require step 4. A little bit later, we're going to bring this up again, and then there will be a new step 4 that will then say, verify whether the location you found is a maximum or a minimum. And we're going to see that there's additional work we can do to verify that part. But as of right now, we're just saying, where are they tangent? Or where are they horizontal? Now, I want to add one more little caveat to this. When you're solving for x, you only have to set the numerator equal to 0. So if your derivative turned out to be a fraction, like the implicit problem we did just a minute ago, where we had square root of y over square root of x, well, that fraction is only 0 when the numerator is 0. Right? We saw that when we did limits. If you got a 0 in the numerator and a constant in the denominator, then the limit was 0. We got into trouble when we had 0 over 0, or we had 0 in the denominator, right? We had to do further investigation. But if the numerator is 0 and the denominator is 5, it's 0, right? So what we do here is, if we have a fraction, right, you only set the numerator equal to 0, But you better check that any values that you find don't also happen to make the denominator 0 as well, right? Because then that may not actually, that's an indeterminate form again. So usually, 9 times out of 10, you'll be just fine if you just worry about this part, right? But you still want to make sure you're checking that you don't have an indeterminate form at that location, because it's possible that the reason you're getting x in the numerator is because the derivative may actually not even be different. The function may not be differentiable there. So you may actually have a 0 over 0 situation, and it may not see that. So make sure that you verify for that. But I think that's what threw a lot of people off when we did the implicit differentiation section. We had you looking for horizontal tangents and vertical tangents. And horizontal tangents, the numerator needed to be 0. Vertical tangents, we were setting the denominator equal to 0. Does that answer? Okay, cool. Yeah.
Could you show us how to find a vertical tangent?
How to find a vertical tangent? Yeah.
Unless it's too small.
It's not. Well, so the vertical tangents are going to occur. It's really the same exact process, except you're setting the denominator equal to 0, and then you're plugging the value back into the original equation to find that location. And so you would verify with the graph itself. But that's a pretty unusual thing to be looking for. But we did say, right, functions aren't differentiable where their tangents are vertical. And really where that came up was the implicit differentiation section, because you were seeing graphs of things that were like ovals and swirls. And, we had some like really funky graphs. And so you could see that there were places where the tangent would be vertical. And so the easiest one I could just kind of do, I can give you an example of a problem that's going to have both, and we can look at how to do both. So and I'm only going to provide the graph here because it really helps reinforce the math that we're doing. So if I give you the equation of a circle, and this would be an implicit function. So we have a circle with a radius of 4 centered at 0, 0. So I know, looking at this circle and the properties of a circle, I know that this is 0.04, this is 0.40, this is 0, -4, and this is -4, 0. So hopefully everybody can see that at the top of the circle, right, we get horizontal tangents. At the bottom of the circle, we'd have a horizontal tangent. But on the sides of this circle, right, you would get vertical tangents if you try to draw the tangent line. So I actually know the answer to this question before I do the math, but I want to show you that the calculus is going to verify this for you. So if we take the derivative of this function implicitly, we get 2x plus 2y dy dx, and on the right side I get 0. If I solve this for dy dx, I can see here that these 2's are going to cancel. And dy dx equals -x over y. So if I want to find the locations of the horizontal tangents, I set the derivative equal to 0. So this guy can only be 0 when x is 0. That's it. So, right, when x equals 0, dy dx is 0. So I actually want to find the locations on the graph itself. So now I go back to the original equation and I plug in 0 for x, and then I solve for the missing piece. So now I'm just going to get y squared equals 16 and y equals plus or minus 4. So you're not done when you get to here. A lot of people try to stop here. If we actually tell you to find the points, well, the x-coordinate was 0. So at x, 0, 4, and at 0, -4, I have horizontal tangent lines. We'll look back at my picture. That's exactly where I predicted they would be. All right? If we want to find our vertical tangents, so the vertical tangents, I'm going to slide this up just a little bit, are going to be when the denominator is 0. And for this guy, well, the denominator is only 0 when y is 0. So when y equals 0, we're looking for points of comma x comma 0. So we plug in y equals 0 into the original equation. We get that x squared equals 16. So x is plus or minus 4. So the points are 4, 0, -4, 0, where the vertical tangents are. And if I go back to the graph, I can see that that's exactly where I was going to get a vertical tangent line. So the issue, though, with these vertical tangents and implicit functions, we saw when we did this section in the book, we gave you some like really tricky problems where the derivative might have given you some of the points that you were looking for, but it didn't always give you all of them. So remember, when you've got a function of two variables, the algebra rules say you need two equations to solve. So you're going to always need to be going back and forth between the derivative function and the original function. But to find a location on the graph itself, you always plug the information into the original function of the graph, because we're looking for an address, basically. That's what the points are. I want to know exactly where on that function this thing is happening. The behavior of the derivative will indicate where to look, right? But then you plug those numbers into the original graph to actually find the address, okay? So it's like doing a Google search. You got to know what to type into the search field, right?
All of this is going on, right?
Mm-hmm. Yep, I'm recording this and it'll be online, so anything you want to keep up with or whatever, that's cool. I can also scan these pages in and put the PDF of the pages up too, so you can actually have the notes in color, yeah. Mm-hmm. All right, what else?
I have a question.
Mm-hmm.
See through the trig derivatives. Like,
Trig derivatives, okay.
what was the purpose of, because like you asked us to write down like sine A plus B or plus or minus B.
What was the purpose of that identity?
Yeah.
So in that section, when we did the trig derivatives, we had you prove, using the definition of the derivative, that the derivative of sine was cosine and the derivative of cosine was negative sine. So when you set those problems up, you got sine of x plus h or cosine of x plus h. And you needed to be able to cancel the h out from inside the sine or cosine function, right? So, and not really even cancel it, but isolate it. So we gave you that, identity, so that allowed you to split up. It was called, you can separate the variables from each other because they were married to each other. And so the sum difference formula let you write all the x's and h's by themselves in trig functions. And then we regrouped it, and then that let us use our special limits to get out of that. Yeah. So that was the only way. If you have sine of x plus something inside the sine, the only option you have is to expand it out. And that really, if you think about it algebraically, was sort of not much different than what we were doing today with the log rules, right? We were expanding out a function to make it easier to deal with each individual piece rather than dealing with it stuck together.
So you would be expected to remember those, like.
I mean, they're considered fair game. They really are. I probably would not make you memorize the identities. I would probably, if I expected you to derive that proof, I feel like there's enough going on there with knowing the limits and the algebra rules that I would probably give the identity as a hint, like maybe just give both and you would have to figure out which one to use and how to use it. But yeah, no, those those proofs are considered fair game, and that's considered a totally reasonable proof to ask a student to be. I mean, I had it on my Calc 1 test at Athens Tech when I took calculus out there. I mean, so
it was considered totally fair game, and I was not provided the identity. But I think given the name, like, just like on the last exam where I said, when you use the definition of the derivative, I actually gave you the answer. Right? So I was like, well, the point is I want to ask you more stuff about this. What if you screw up part A? At least you know you've got the answer to continue on with B and C, right?
So like what type of problems? I mean, because I know we did fees.
Those are it. Those are the two.
Those are the only two?
Those are the only two we do that for, because the other four trig functions, their derivatives we can derive with the quotient rule. So if you go back and look at that assignment, in the video assignment, we used the quotient rule. We said, let's just take for granted that this is the derivative of sine and cosine. And we use the quotient rule to derive, I think, secant, derivative of secant, derivative of like tangent. And then in your practice on your own, we had you do the other two. Or in class, then, yeah.
Oh, okay. So like these questions are just like the only.
Yeah, the definition of the derivative in terms of trig functions are isolated only to sine and cosine. And then the other four you can generate using the quotient rule, because you can rewrite them in terms of sine and cosine. Yeah, we would not ask you from, because there is a sum difference formula for tan of x plus h, but it's really, really gross. And it's just a nightmare proof to do. It's just too beyond the pale. Yeah. So I'm going to make a note of that on here in terms of trig derivatives. Right? Only sine and cosine, right, using the definition of the derivative. That's the only thing. The other four can be derived using the quotient rule. And I think it's silly I don't think it's test level question. I think it's too easy to ask you to use the quotient rule to prove one of the other trig rules. I think that's just kind of silly exercise to do on an exam. I would much rather give you functions with trig functions in them and have you use just the rules to do it. Now, the reason that I said this is so useful to you is what if you forget? Or what if you're not sure? I can't remember if this one's positive or negative, or I'm just not sure I'm plugging the right thing into the right spot. It's very comforting to know that there's a very simple process you can do to check if you're using the right derivative. So as long as you know, you can write everything in terms of sine and cosine, the quotient rule will give you the appropriate derivative that you need. And so I'm very bad at memorizing things, so I'm very comforted when I know there's a really easy way I can check myself some other way to know that I've done it right, because I'm the queen of substituting the wrong thing at the wrong place. I'll just transpose things on tests because I get in a hurry. But the derivative of any trig function that starts with the letter C is negative. The rest of them are positive, unless there happens to be a -1 out front of the problem you're doing, right? And you'll see tomorrow in class, even the inverse trig functions, that rule still holds. The ones that start with letter C are negative, the other ones are not. There's patterns everywhere in the trig stuff. The more patterns you see, the easier it is to memorize stuff. If there's anything in your workbooks you didn't get to, y'all, anything is fair game. So whatever's bothering you, I want to talk about. I just don't know what's in your head unless you tell me.
On number 7 for our classwork, under the chain rule, it asks to solve for G prime of A and F prime of A, and it gives you FA equals pi over 4, cosine A equals 1/2, F prime of A equals -3.
Yeah, this one kind of quick.
Okay, so I'm going to put this under here real quick. So we're talking about this problem on page 129, right? So it's number 7 And we asked you to use this information provided, right, to find these two derivatives. So what I'm going to do is write this down and walk you through it. So what we gave you in the problem, and it was a little confusing because we had the capitals and the lowercase, but we said if capital G of x is defined as sine, right, of f of x, and capital F of x is defined of f of sine of x, we wanted you to find the derivatives given the following information. So we told you that little f of a is pi over 4. Cosine of a was 1/2. F prime of a was -3. And f prime of the sine of a was 10. So what we were doing here was we were giving you a chain rule problem where we wanted to know if you could follow the procedure, right, without there being functions given. Did you really understand procedurally what to do with a chain rule problem? So the first thing that's really helpful with these is find G prime, capital G prime of A, and F prime of A by first finding the derivative of the function. So capital G prime of X, we say, well, we want the derivative of the outside function, and the outside function is sine. So the derivative of sine is cosine, right? And then you leave the inside alone. Then you multiply that by the derivative of the inside. And the derivative of the inside is just f prime of x. That's the best we can do. So now, if I want to know what G prime of A is, well then everywhere I have an x, I just plug in an A. Now I'm ready to run down my list and fill in what I need. So cosine of A is given, right? But f of A is pi over 4. So a lot of people would mistakenly just put 1/2 here, and that was not true. It was cosine of f of A, and when you do composite functions, you work from the inside out. So cosine f of A was pi over 4. F prime of A was given as -3. So because this is one of your special angles, we expected you to actually know that value, and this is square root of 2 over 2 times -3, so it was a little bit easier to read if we wrote it like this. So a wrong thing to do in that middle step would have been to put 1/2 there and not pay attention that wasn't cosine of A, it was cosine of f of A. If we want to do capital F prime of x, well, the outside function here is f. So we just take the derivative of the outside, right, leave the inside alone, and then multiply by the derivative of the inside, which is cosine of x. So now when I plug in A, and I think what made this problem tricky for a lot of people was they tried to combine steps. If you're not sure about these conceptual questions, literally do it piece by piece by piece, and you just copy down what's next. So now if I look at this, well, sine of A, right, is not given, but f prime of sine of A was given, and it's 10. We actually gave you that entire piece. Cosine of A was given, and that's 1/2, so then 10 divided by 2 is 5. So in order to properly apply the chain rule, you need to know how to read composite functions, and that's why I really, really enjoy the sandwich car truck soup problem, because you get these kind of ridiculous answers, but you end up getting the right answer if you can procedurally read the composite functions correctly and see what turns into what. Does this make sense? Okay.
Can you go to number 8?
Yeah. All right, so number 8 in that same section. I'm gonna borrow 129. Have it open, sorry. Not too many percent change to it. All right, so in number 8, same section, we were given that the derivative of car is truck, and the derivative of soup was sandwich. And we were asked to differentiate the following things. So for A, y equaled car of x, right, quantity cubed. So the idea here was, can you identify the outside and the inside function? So the outside function was some stuff cubed, where the stuff inside was car of x. So then the derivative of the outside function was 3u squared, and the derivative of the inside function came out to be truck, because we were told derivative of car is truck. So then when we put it all together, y prime is 3 car of x quantity squared times truck of x. So it's f prime times u prime, derivative of the outside times derivative of the inside. And so remember, chain rule is the ultimate procrastination tool. You just start from the outside and you just see, you kind of zoom way out, you just see, I see a bunch of stuff cubed, so I'm just going to deal with that first. And then you zoom in and look at the inside. And if you have a nested chain rule, right, we just start from the outside, we break it down, keep punning, right, and then slowly build it back up on the other side. All right, so B said, well, h of x is soup of x to the 4th. So this was a different notation, right? The first one we took the entire function and cubed it. Now we only are taking the variable inside and raising it to the 4th. So now the outside function is soup, right, of u. Soup is the outside. And the expression on the inside is x to the 4th. So the derivative of the outside, well, the derivative of soup was sandwich. And the derivative of the inside is 4x cubed. So if I apply f prime times u prime, right, h prime of x was sandwich of u, which was x to the 4th, times the derivative of the inside, which was 4x cubed. And the last one, it's my favorite one, is y equals car of soup of x. So here, the outside function is car of some stuff. The inside function is soup of x. So the derivative of the outside is truck of that same stuff, and the derivative of the inside is sandwich. So then when we take the overall derivative, right, it's f prime, so truck of u, and u was soup of x, times u prime, which was sandwich of x. So if you come up with a way to systematically break it down, it's really more important that you know the procedures to follow, you know, and then hopefully if you know the algebra will follow. But, you know, when you get really good at these, you can sometimes just throw it together. But I still find if I'm taking an exam and I know I have a systematic way to make sure I'm organizing everything, it doesn't take me very long to do that. And then I just move on from the problem because, like, I know I'm right. But, you know, it's sometimes where people try to work in a hurry and they think every little time they put their pen to paper, they're wasting time. But not really. If that time is very efficiently spent, it actually makes the calculation of the problem really quickly because I know I'm just multiplying these two things, right? Does anybody have any questions about how I broke that down? Does it make sense? Okay. Okay, hang on. Alex had his hand up first, and then I'll come back to you. No, you got one? Okay, go for it.
Okay, can you do number 3? Oh, there's an implicit differentiation. It's 2xy.
Wait, hold up. All right. No, this is a good exercise. Can you? All right, so 2xy.
Oh, wait, that's not a guided exercise. What I just asked. Wasn't a guided exercise, I just asked it.
Oh, it was a guided exercise?
Yeah.
Okay.
I just got confused, like, I'll just ask a general question. When you plug in dy dx, you don't replace the y term. You just like put it next to it and you solve for it. 'Cause that's what
Yeah,
I've messed
you,
up.
because you're doing chain rule, so that's your multiplying times the derivative of the inside. The derivative of the inside is dy dx.
Okay,
So that's your u prime, every time. Yeah.
okay, that's fine.
Mm-hmm. All right, go ahead. Did you have something?
No, it's okay. Okay.
Good time.
Would you mind doing page 127?
Yeah. What was that? Was that the chain rule stuff?
So it's basically like it's doing it like 3x.
Mm-hmm.
These 3x power, I guess.
So that's the same thing we did at the very first question.
Yeah, I'm sorry.
So it's you take e. Wait, was it 3 you said?
3x.
Okay. So 3 to the what?
Just
Oh, that's the proof problem.
yeah.
Okay. Yeah, I'll talk to you. Okay, well, actually, I do want to make some comments about that problem. So what we asked you to do in that was we were asking you to derive the derivative of 3 to the x. So this is the same way when we did the limit definition of the derivative. The first day we did it, we had you calculating the derivative at specific locations, right? And then we backtracked and said, now calculate the derivative at all the locations on the graph, right? And that's when we backtracked to f of x. So here, we don't have a rule for this. This is kind of touching on what we did today. So what we do here is we used the fact that this function has an inverse in order to calculate its derivative. And so we started with the concept of, right, let 3 to the x equal something e to the w, and we said solve this for w. So you solve this for w by taking the natural log of both sides, because that's the inverse of this e function. So we ended up getting, right, the natural log of 3 to the x equals the natural log of e to the w, and that's how we ended up with w equals natural log of 3 to the x. However, we said, well, if we bring the x down front, it's going to be a little bit easier when we have to take the derivative, because if you still leave it up in the exponent, you're kind of back in the same issue that you started with. So then we, sorry, remind me what step 3 of that problem was. That was, I think, A and B. And then what was the directions for C?
Oh, y equals, sorry.
No, you got it in front of you.
Y equals 3x, and by instead differentiating, y equals e to the w.
Yeah. So if you start now with the e to the w, what we wanted you to do was plug what you just found for w, right, into that guy. So now if you've created a chain rule problem for yourself, so now if you take the derivative of the left side, right, you're just going to get y prime or dy dx, and then on the right side, this is a chain rule, so you get e to the u times the derivative of what's inside here, and the derivative of that is just natural log of 3, because the derivative of x is 1, and that's just a constant. So then we said, well, plug back in what e to the w was, because that's all this is e to the w, right? And e to the w was just 3 to the x. So on the very next problem, we did the same procedure for a to the x, and we saw that the derivative of a to the x ends up being a to the x natural log of a. So this still holds. So this is for any base a, right? We did it specifically with 3. It's for any base a, and we saw that this actually even holds when a equals e, because if you have e to the x, what you're really getting is this, but the natural log of e is 1. So that's why e to the x is just e to the x. So it's the same kind of concept. Let's do it with a specific base. Now let's do it for any base, and we see that even e, right? Any real number holds when you plug it into this equation. And so that was the idea to derive it. But now you're just able to know it. So one more thing before some people start getting out of here that I want to mention that is good to do when you're kind of studying and going through stuff is I used to do this in my own calculus notebook, and I just kept adding to it. So in this unit, right, we've done shortcuts to derivatives, right? It's good to have like a list for yourself. So we've done power rule, right? There's a rule for constants. There's the constant multiple rule, right? Product rule. Quotient rule. Chain rule. And kind of under the chain rule, kind of inside the chain rule, implicit differentiation, right? Logarithmic differentiations. Those are both kind of spin-offs of the chain rule. You should make sure that you know the process and the procedure for each one of these, because these are the ones that require like a process, right? But then within those, kind of separately, I used to like to make myself a 2-column chart, and we're going to keep adding to this. So these are the derivatives that you should have like memorized, right? So obviously we want sine, cosine, tangent, right? Keep listing all the trigs down. Then we have e to the x, natural log of x, right? A to the x, log base a of x. So as we start in deriving these guys that you have to memorize, I used to have like a little 2-column chart, and I would just take a piece of paper and fold it in half and just start adding to my list as I went down, because when we get to unit D and we start doing antiderivatives, this thing will come in really handy, because then instead of going from this side to this side, you're actually going to start on this side and go back to this side. So anything you have to memorize the derivative for, you're expected when you see it's the derivative to know what function gave you that derivative, right? So this is a good thing to do. And so like, for example, e to the x, right? This is 1 over x, a to the x, ln of a, right? 1 over x, ln of a. And so then tomorrow we'll do the inverse trig functions. We're going to do more functions. So you should just keep adding to this list, and it's just a good thing to have as we move forward, so you kind of know what I need to memorize. And so I might make a study sheet where I have all of these things listed out, and then maybe notes of the process, right, to myself. And then on these, I would just have a list with their corresponding derivatives. So I just have it to look at when I'm doing problems. And then I would slowly like memorize things if we need it. All right, so it's 4:30, but I'm not rushing anybody out of here. I can stay till 5. So if you did not get all of your questions answered, you can stick around. I know some of you have somewhere to be. But if anybody's got more questions, we'll keep doing it. But if y'all have to go, just go ahead. You're fine. Yep.
Okay, so number 5, this is still the chain rules.
Mm-hmm.
It says differentiate function f of x equals 5 sin x. Do we like use one of these equations over here?
No. So what we did on the page before was you were deriving this for any A.
Oh, okay.
So now what we said, and this is what I was mentioning before, the first thing we're gonna do when we give you some new rule is then we're gonna throw it with the chain rule at you, right? So if you have 5 raised to the sine of x, right? Well, the outside function was 5 to the u. The inside function was sine of x. So the derivative of the outside is 5 to the u ln of 5. That came from right here. That's the derivative of any function a to the x. The inside function u prime is cosine x.
Okay, so, like, where is the u coming from? Are you just replacing?
So
X with U?
so F and G, I don't like to use that for chain rule personally because I associate that with quotient and product. And because I'm doing a different thing with them, I like to just use a new letter when I'm using chain. So for me, it's like, okay, chain rule, U is gonna stand for, it's an expression of X, right? And so I'm saying, because it's sort of a different thing when we set it up, right? We only multiply these two pieces together for chain rule. And so that's what I'm saying is, the derivative here is, the outside is just F5 to some stuff. So the derivative is 5 to that stuff, ln of 5. And then here's the derivative of the stuff.
Okay.
Yep. And so then when we put it all together, right, you get 5 to the sine x ln of 5 times cosine x.
Okay, so when you do that,
Mhm.
it's always, like, if you're gonna have a number and, well, if you have like, just like, I don't know, 6u, it's always gonna be a to the x ln
Mm-hmm.
a? Okay, because that's where I got confused.
Yeah, and that's why I said doing something like this is really helpful because it just organizes all the functions you're supposed to know the derivatives for. And so what I would probably do is put the a to the x under e to the x, right? And then the ln of x and the log of a under each other. I'd probably have, but yeah, it's just really helpful. And then you can look things up until you've really got them down. It helps organize it. And you know these are all the things I better have memorized.
Oh, can you do the other one on the page, 3 tangent, and then it's,
That triple chain rule
Yeah,
one?
yeah.
Mm-hmm. So the other one was tangent. Wait, what was it? What was the base?
3
Uh-huh.
tangent, x squared plus 5.
Okay. So this one, the outside function was 3 to the u, and the inside function was tangent of x squared plus 5. So the derivative of the outside function is 3 to the u ln of 3.
Okay.
The inside function, well, you have another chain rule here. So the derivative of the outside is secant squared of that stuff, and then we have to multiply it by the inside. So now the entire derivative is 3 to the tangent, because we got to do the u, x squared plus 5 ln of 3 times secant squared of x squared plus 5 times 2x.
Okay, I get it. Because I wasn't using u, and I was just like, oh.
And it still works with F and G, but then you got to remember midway through what rule you're using, and it's, oh, in that case, it's F prime times G prime, right? And so I just find that sometimes it's better to just, throw a new letter. And some textbooks do that, some don't. I just kind of grew up in the U. And then later when we do, Unit D, we're actually going to do something called U substitution for antiderivatives. And so in my head, just from my math classes, I'm just sort of programmed that U is sort of like a stand-in. We kind of use it when we punt things. We're like, okay, it's U of this stuff. We always use the letter U because no one ever names a function U, right? And so I always know it's temporary. And I always, and if I see U in the final answer, I know I better plug something back in because U is a placeholder for me. But you can use whatever letters you want. I mean, these letters are arbitrary. Yeah.
Do you have any advice of being able to look at a problem and identify oh, this is just the product rule, or this is a chain rule with a product rule inside it?
Yeah, so it just takes practice. And so one thing that I would really recommend doing is, this is where like you can find textbooks online or a textbook, but sometimes you can just like look up old exams or whatever, but